different ways that there can be heat flow from one object to another, ways that thermal energy can be transferred. Before we do that, uh, heat, thermal energy is a form of energy, of course, and there are a couple different units that are used. A calorie is a unit of energy that's used frequently in food, and just so you know, a calorie is equal to 4.186 joules. There's also another unit, the British thermal unit, BTU, which is 0.252 kilocalories, which is 1,055 joules. So there are a couple different units that we can use. In all of our equations, heat will be the variable Q. And remember, when we say heat, we mean how much energy is transferred from one place to another. It's not how much energy something has. And the unit of heat is an energy, of course, so it's an energy being moved, and so our SI unit is joules, although we could use calories or BTUs as well. There are a couple things related to how quickly energy is transferred from one object to another. Remember, whether energy is transferred only depends on temperature. Energy will always flow from higher temperature to lower temperature. Spontaneously flow, I should say. You can do things to make it go the other way, but But heat capacity is one thing that determines how fast it will flow. Heat capacity is capital C, and it's defined as the amount of energy being transferred, or an amount of energy per a change in temperature, temperature in Kelvin. So heat over temperature, so the unit of heat capacity is joules per Kelvin. So it's how much energy it takes to change the temperature of a given sample by however much. How much energy is required to raise the temperature of a given mass. Now notice there's no mass in here, but it's kind of hidden because heat capacity is not a property of a material. It's a property of a given sample of a material. So the more mass you have, the greater heat capacity you're going to have, because it takes more energy to change the temperature of a larger sample. Specific heat is closely related to heat capacity, but specific heat is the property of a substance. It is, as I said, very closely related. It's the heat per mass times the change in temperature. And therefore the unit, again, it's not very nice, it's just joules per Kelvin times kilogram. There's a table in your book on page 553 that lists specific heats for a lot of different stuff. And this is a property of a material. So this tells you how much energy it takes to, the specific heat is how much energy it takes to change 1 kilogram of your sample by a temperature of 1 Kelvin. Most of these you can just look up in the table. You should probably memorize that for water, the specific heat is 4186 joules per Kelvin times kilogram. That's one that you're going to use a lot. So even just for doing your homework, it's worthwhile to remember that. And I don't know, I might make you memorize it for a quiz and test. So if I ask you, how much energy is required to raise the temperature of 3 kilograms of water by 2.1 Celsius degrees. This is just a simple application of our specific heat formula. Water has a specific heat of 4186, and we set that equal to Q over mass times. And the change in temperature is in Kelvin, but remember the Kelvin scale is the same size as the Celsius scale, so a change of 2.1 Celsius degrees is the same thing as a change of 2.1 Kelvin degrees. So you can just say times 2.1, and thereby figure out how much heat that, or how much thermal energy that takes, how much heat, I guess it's how much heat transfer that takes. And that comes out to 2637.8 joules of energy. Alright, so that's what specific heat is. And specific heat, as I said, a higher specific heat means that it takes more energy to change the temperature. Water has a very high specific heat, and that's responsible for many of its properties, and also many things that we observe in nature, particularly with regard to weather, which is something that we'll get to in the next video. I'm going to talk about a weather-related thing that is caused by specific heat. Calorimetry is an application of the concept of specific heat. What happens with a calorimeter is a thermally isolated container, and usually it's filled with water, just because the specific heat of water is known and water is very easily available. Right. So what you do when you're doing calorimetry is you drop an object into this thermally isolated container and then just wait a while and see what the final temperature is. And by doing that, you can figure out what the specific heat of the object you dropped in, if you measured its temperature beforehand, or if you know what the substance is, you can figure out its temperature, original temperature that way, and so forth. So what's happening is that, there's no, and you put it inside an insulator. You can do a very simple one. It's just like a styrofoam cup and water. And maybe you've done that in chemistry class. But if it's thermally isolated, then the heat flowing out of the object is flowing into the water. And so there's no total change in heat. So Q, heat, it's heat transferred, right? It's energy transferred. So if we have the energy, if we drop a block in, so we'll call it block, there is no heat entering the system, so the heat flowing out of the block has to be equal and opposite to the heat flowing out of the water. Whatever goes out of the block goes into the water. Or if the water is lower temperature, if the water is higher temperature, energy will flow from the water into the object. And so if we rearrange our specific heat equation, Q would be equal to Cm delta T. So for our block, that's C block, mass of block, delta T would be T final minus T block. And I'll call it T block because it's initial. Final, eventually when they reach thermal equilibrium, and that's what, when you do calorimetry, you're dropping it in and you're waiting for thermal equilibrium. But once they're in thermal equilibrium, the water in the block will be at the same temperature, and so this T final is the same for both. And then we have specific heat of water, mass of water, times temperature final minus initial temperature of the water. And so, as you can, we can use this equation to figure out what the specific heat of the unknown is. Oftentimes, you want to solve for the final temperature. If you want to solve for the final temperature, you do some algebra, and it comes out to look like this beautiful equation. And by beautiful, I mean obnoxiously long. C block plus mass of water, C of water. This might look like a pattern. This might look familiar because it's kind of the same format as our velocity of center of mass equation, and also pretty similar to our location of the center of mass equation. So let's try an example of a calorimetry problem. common type of calorimetry problem where you want to find the specific heat of the unknown. So you have a sample of an unknown substance with mass 45 grams and temperature 35 degrees Celsius. It's dropped into a calorimeter containing 100 grams of water at 20 degrees Celsius. After a long time, the temperature of the water becomes 23 degrees Celsius, where they both equalize at 23 degrees Celsius. And we want to find the specific heat of the unknown. Well, just plugging into our equation, we've got the specific heat of our block, which in this case is our unknown, mass of block, temperature, following the pattern, following this equation. The specific heat of the unknown, that's what we're trying to find out. The mass of the unknown we know is 45 grams, and we're going to be dividing out, we're going to divide that mass over the other side, and that'll cancel out the mass of water, so we don't need to worry about converting to kilograms. And then we have the change in temperature of the block. Well, the final temperature is 23 degrees, and the initial temperature was 35 degrees, plus specific heat of water, 4186. Mass of water is 100 grams. Final temperature is still 23, initial temperature 20. And this comes out negative, but when we move this over, it becomes negative, and the negatives go away. 0. And we punch all that junk in, and the specific heat of the unknown comes out to be 2325.5, repeating, as it turns out, joules per kilogram times Kelvin. That's specific heat of unknown times mass of unknown times the change in temperature of the unknown plus specific heat of water times mass of water, change in temperature of water, plug all that in, comes out to 2325.5, repeating joules per kilogram Kelvin. So that's an example of a problem that applies specific heat, specifically calorimetry.